Hello, this is Jude Socrates. Welcome to today's video where we will talk about the span of a set of vectors in R3. Now, of course, last time we saw the span of a set of vectors in R2. So if you haven't seen that video yet, please do so now and then come back because we are going to build on what we saw in that video. So first, let's recall what is the general definition of the span of a set of vectors. So, if S is the set v1, v2 through vk, and these are vectors from Rn, then their span is the set of all possible linear combinations in this set. So we write this symbolically as the span of S, or the span of v1, v2 through vk, as the linear combinations x1, v1 plus x2, v2, all the way to xk, vk, where the coefficients x1, x2, through xk are all real numbers. So we said that if you set a coefficient equal to 1 and everything else equal to 0, then you will get v1 or you will get v2. In other words, you can get each of these individual members automatically as part of their span. And if you make all of the coefficients 0, then of course you just get the 0 vector. So therefore the 0 vector is also automatically a member of the span of any non-empty set of vectors. So we started off last time by looking at sets where there was only one vector. So in this case, the span of S is all the scalar multiples of V, which we write as T times V. And when we looked at the vector v5, 2, then we said that the span of that single vector 5, 2 is just the line y equals 2/5 x from R2. So naturally now we want to ask the question, well, what does the span of a single vector look like if that vector is now from R3 instead of R2? So here is an example. We have a vector u, the vector -5, 3, 2, and we'll make the span of u. So again, that's all the scalar multiples t times -5, 3, 2, where t is a real number, and we can bring that scalar inside the vector, so it just becomes -5t, 3t, and 2t, where t is a real number. So let's begin by computing some members of this span. So I'm using the software Scientific Notebook that you see up here, and it allows us to make computations on vectors and matrices. So here is our vector, and by writing 2 times that vector, I can just click on this equal sign, and there miraculously is twice the vector. So we get -10, 6, and 4. And we can keep doing this. We can also get, for example, how about -3/2 of this vector? So we get 15/2, -9/2, -3. Now, if you don't like fractions, we can also click on this button, which gives us an approximation. So we get 7.5, -4.5, -3. Okay? We can also do -2u. So let's put -2 times this vector. And we get, of course, +10, -6, -4. Now that's great, of course, but what we want to do is look at these vectors. What do they actually look like? So here we are back in GeoGebra Classic, and this is our welcome screen. So what we have to do first is change to 3D graphics. So we click on this button, and there's our 3-dimensional coordinate system. Now, the thing about GeoGebra is that its default 3D picture has the positive x-axis in red going to the right, and the positive y-axis here in green, and the z-axis, positive direction, is blue, pointing upwards, of course. I like to turn this around, so all you have to do is grab it with your left mouse button and then turn it around like this. So now our positive x-axis is on our left, positive y on our right, positive z going up. Z is always going to point up in the positive direction. So our vector u is the vector, and remember you have to put an extra pair of parentheses inside, -5, 3, 2. Aha! So there's our vector, and again we can spin it around a little bit, and we can see what that vector looks like from different perspectives. Okay, so again let me change that color so we can track it later on. So let's turn that red. You probably knew that was what I was going to choose. Okay, so let's draw the vectors that we just computed. Let's say w1 equals 2 times u. So there it is. As expected, it's twice the length of that vector and pointing in the same direction. And w2 is -3/2 u, so we can write it as -3u over 2. So now it's pointing in the opposite direction. And we also did w3 equals -2u. And how about w4 equals 2.3u? Okay, that's a little bit off screen, so how about 1.3u? Okay, there you go, we can still see it. And w5 equals, how about -0.72u? Okay, so we have several vectors here, but just like what we saw in R2, if you turn our system around, we're still getting something that looks like a line, right? I think any reasonable person will call that object a line. And any way you look at it, it still looks like a line. Okay, so let's go back to Scientific Notebook. Okay, so we're back. And the next logical question that we're going to ask is, can we make an equation that describes the vectors x, y, z, which belong in the span of the single vector -5, 3, 2? So when we were in R2, we got something like y equals 2/5 x, right? So can we get an equation similar to that now that we are in R3? So let's try to do the same strategy that we did back in R2. And that was, first, let's give it a name. So x, y, z will be -5t, 3t, 2t. Okay? Then we can solve for each of the three variables. X is just -5t, y equals 3t, and z equals 2t. And then from each equation, we can solve for t. So now we get t equals x over -5 for the first equation, t equals y over 3 for the second, and t equals z over 2 in the third. So in R2, we kind of stopped with just x and y. And we said, okay, y would be -3/5 x in this case. But there's a third variable here, z. Okay, so should we also solve for z in terms of x or z in terms of y? So unfortunately, we're not going to do that. Okay, that's a little bit too cumbersome. So what we're going to do is, well, we're going to give these equations names. Okay, so the vector form for the equation of a line would just be what we started out with. So x, y, z is -5t, 3t, 2t, where t is a real number. Parametric form, just break down that single equation into three equations. So x is -5t, y equals 3t, and z equals 2t. Parametric form, we're going to just keep these three equations. So even though there are two equal signs here, there are actually three equations, because x over -5 is y over 3, y over 3 is z over 2, but x over -5 is also z over 2. Okay? Now, notice that we were able to do that because none of the components of u was 0. Okay? Now, we noticed that when we drew the picture in GeoGebra, we got a line, and we can think of the vector u as the direction that that line is pointing to. Okay? So we call that the direction vector, or rather a direction vector for that line. All right? So if none of the components of that direction vector is 0, then we can solve for t in all three components to get the parametric form. Notice also that if one of them were 0, then if you multiply that vector by any scalar, you'll still get 0. Okay? So either none of those components are 0, or at least one of them is 0, and no matter which direction you pick, that component will stay 0. Okay, so we can generalize this even further. What about Euclidean spaces that we cannot visualize, like R4, R5, and so on? So we will say that if V is from Rn, and it is a non-zero vector, then the span of V is geometrically a line L in Rn. And it passes through the origin. As we saw in R3, that line passes through 0, 0, 0. So even though we can't visualize R4 and R5, if you have a single non-zero vector, and we find its span, all of its scalar multiples, then we'll just call that a line in Rn. But if we're in R3 and our vector is ABC, then our line has vector equation xyz equals t times ABC, where t is a real number. And again, we can separate the three components to get parametric equations: x equals at, y equals bt, and z equals ct. Okay, great. So now our next question is going to be, well, what if there are two vectors? Okay, we did this also in R2, and in our last video, we looked at two vectors, 5, 2, and -1, 4, and we showed that the span of these two vectors is all of R2, meaning every vector xy in R2 can be written as a linear combination of u and v. So in fact, here is the screen from last time. Here are u and v in red and blue, and we made several linear combinations. And we said, if you keep filling up the screen with linear combinations, you're going to eventually cover the whole screen. So we proved by algebra that no matter which vector xy you picked, you can find coefficients r and s so that xy is a linear combination of these two vectors with coefficients r and s. Now, the reason why that worked was because u and v were not parallel to each other. So we can say this in general, that for two vectors in R2, if they are non-parallel vectors, then the span of those two vectors is all of R2. In other words, if you pick any vector xy in R2, then you can find coefficients r and s so that that vector xy is a linear combination ru plus sv. And you will be proving this theorem in exercise 10 of section 1.2. Okay, so now let's see what happens if u and v are now two vectors from R3. So we have made these two vectors from R3, and we have u is 3, 2, 1, which we write again as a row matrix, and v is -1, -5, 2. And the span of these two vectors are all the linear combinations of these two vectors. So let's make some linear combinations of the span of u and v. So how about, what if we just add them together? So here is u, and we will add v, and we will get that vector. Okay, how about u minus v? So we will take these two vectors, and then instead of adding, we will subtract. And we get that vector. Okay, how about u plus 2v? So now that's a new linear combination, and we are going to get that vector. Okay, so again, that's nice, but we want to look at these vectors. So let's cut again back to GeoGebra. Okay, so here's a new copy of GeoGebra, and I've gone ahead and input our U and V, and they're in red and blue. So let's make some linear combinations. We have W1 equals U plus V, W2 equals U minus V, W3 equals U plus 2V, W4 equals minus U minus 2/3 V, so I'll write that as 2V over 3. And then W5 will be, how about negative 3/2 U minus 3U over 2 plus V. Okay, so you have 5 linear combinations of these vectors along with the 2 original vectors. And again, they look like they're pointing in random directions. Okay, but how about if we look, let's say, over here, from this perspective. So it looks like they're not so random at all. In fact, if we look this way, it almost looks like they're forming a line. Okay? In other words, it looks like they're parallel to each other. But of course, no. If you look this way, they're definitely not parallel to each other. So we saw that no matter how you look at a line, no matter which direction you look at a line, it still looks like a line. Okay? But these vectors, from one perspective, they look like a line. But from another perspective, they're not. So, of course, something different, something new is going on here. And it looks like only certain vectors in R3 are linear combinations of these 2 vectors. Okay, so there seems to be something special going on with these linear combinations. So, to understand what's going on with the span of these 2 vectors, let's see if we can try to make an equation that describes the vectors that belong to the span of these 2 vectors, just like what we did for the span of one single vector. So again, let's give it a name. Let's call x, y, z as the linear combination r times 3, 2, 1 plus s times minus 1 minus 5, 2. So our problem now becomes, if you're given any vector x, y, z in R3, can we always find coefficients r and s that satisfy this equation? But if not, what condition or conditions should the coefficients x, y, z satisfy so that it is possible to find r and s? Okay, so for reasons that we're going to see a little bit later, our first question is going to be, is it possible to find 2 distinct solutions for r and s? Okay, what does that mean? In other words, can we find 2 pairs of numbers, r1s1 and r2s2, so that xyz is the linear combination r1 times 3, 2, 1 plus s1 times minus 1 minus 5, 2, but also xyz is r2 times 3, 2, 1 plus s2 times minus 1 minus 5, 2. Are there 2 pairs of coefficients that can give us the exact same vector? Okay, so that's the key. We have 2 equations for the same vector. But of course, what that means is that these 2 linear combinations should be equal to each other. So we will get this equation. We will get that r1 times 3, 2, 1 plus s1 times minus 1 minus 5, 2 must be r2 times 3, 2, 1 plus s2 times minus 1 minus 5, 2. Okay, so what are we going to do? Let's put the first vectors together. So we have r1 minus r2 times 3, 2, 1. And let's put the second vectors on the other side. So we have s2 minus s1 times minus 1 minus 5, 2. Okay, so we're assuming that there are 2 ways to do this. So in other words, either r1 is different from r2 or s1 is different from s2. two different answers. Okay, but what's going to happen? Well, let's see. If R1 and R2 are different, then R1 and R minus R2 is a non-zero number. And recall from chapter 0, when we talked about the 11 field axioms for real numbers, then R1 minus R2 will have a reciprocal. So we can divide both sides of that equation by R1 minus R2. So we get that the vector 3, 2, 1 is S2 minus S1 over R1 minus R2 times minus 1 minus 5, 2. Okay? But we said that when is a vector a multiple of another vector, that's how we define parallel vectors. So this tells us that this vector is parallel to this vector, but we saw from the picture they're obviously not parallel to each other. How can you possibly get this vector as a multiple of this vector or vice versa? That's not going to happen. So R1 and R2 have to be the same. And what else is going to happen? Well, this time if S1 and S2 are different, we can divide both sides by S2 minus S1. So again, we get that the two vectors are parallel, which again, that's not true. So we can now conclude that if there is a solution R and S to that equation, then R and S have to be unique. There's exactly one value for R, one value for S that will solve us this equation. Okay, so now we're ready to solve for R and S. Okay, and as before, we are going to set the components equal. So X is 3R minus S, Y is 2R minus 5S, and Z is R plus 2S, all right? So we have three equations in R and S. We want to solve for R and S. So again, to do that, let's use the addition method, just like we did in the last video. So there is already an isolated R in the third equation, so we can use that to eliminate 3R from the first equation and 2R from the second equation. So we're going to do two things. We're going to multiply the third equation by -3 on both sides and add to the first equation so that we can get rid of R in those two equations. So here we have it. We have -3z minus 3r minus 6x, and we will add it to x equals 3r minus s. So we have these two equations. Adding them together, you get x minus 3z on the left, and on the right, what survives are minus 6s minus s, which is just minus 7s. So we now have s, which is x minus 3z all over minus 7. So now we'll do the same for y, right? So we will multiply both sides of the equation for z by -2 and add to the equation for y. So here they are. You get -2z is minus 2r minus 4s. Add to the equation for y, and we get y minus 2z is minus 4s minus 5s, or minus 9s. And we get to solve for s again as y minus 2z over -9. So at this point, now we are going to use the uniqueness of the solution. We said earlier that if we can find r and s, then there's only one possible value for r and one possible value for s. But wait a minute, s is this expression, but s is also this expression. So what has to happen? These two expressions have to be equal to each other. Okay, so we have s is x minus 3z over minus 7, has to be the same as y minus 2z over -9. So we clear the denominators. We multiply x minus 3z by -9 and y minus 2z by -7. So we get minus 9x plus 27z has to be equal to minus 7y plus 14z. So we have two expressions for z here. We'll put them together. Let's put all the variables on one side, and we get minus 9x plus 7y plus 13z has to be 0. Now, this equation is, of course, very special. And if you did not have the z here, if you only had x and y, what you get would be equivalent to the equation of a line in R2. But we're now in R3, so there's a z. And we call this a Cartesian equation for the span of those two vectors. Now, because we have GeoGebra, let's type in this equation in GeoGebra and see what it looks like. So our equation is negative 9x plus 7y plus 13z equals 0. Ooh, okay. So there's this fuzzy thing that has appeared on the screen. And if you turn it around like we did earlier, ooh, it seems like all of the vectors that we computed earlier are on that mysterious thing. Okay, so you probably know that that mysterious thing is not really that mysterious. We call that a plane. Okay, so it's a flat surface. It's like a sheet of paper, and it's kind of transparent. And that's because it has no thickness. Okay, it has the thickness of a point, which is really no thickness. So all of the vectors that we have plotted so far, all of those vectors are lying on that plane. So let's summarize what we did so far. What we showed is that if we can find R and S, so that x, y, z is R times u plus s times v, then the components x, y, and z must satisfy the Cartesian equation minus 9x plus 7y plus 13z equals 0. Okay? But what about backwards? Okay? Now let's also prove the opposite direction. If x, y, and z satisfy this equation, does it mean also that x, y, and z can be written as a linear combination of these two vectors? So this is like the problem that we saw in R2. If you have all linear combinations of those two vectors, you will get the entire plane R2. Okay? So this time, if you have any vector which lives on that blue plane in R3, can we find coefficients R and S so that that vector is a linear combination of those two vectors with the coefficients that we found? So here's the problem. We will now show that if x, y, and z satisfy the equation minus 9x plus 7y plus 13z equals 0, then we can find R and S so that x, y, z is R times 3, 2, 1 plus S times minus 1 minus 5, 2. So how are we going to do that? Well, we are given this time that x, y, and z satisfy this equation. So we can solve for any of those variables in terms of the other two. So how about z? So we can solve for z isolated, 9x minus 7y on the other side, all divided by 13. Now we solved for s last time. S was x minus 3z over negative 7. So we can plug in that value for z into that equation, and we can ask Scientific Notebook to compute that for us. We just get 2 over 13x minus 3 over 13y. Okay, so from our first equation for x, we also got that x is 3r minus s. So now that we have s, we can solve for r from this equation. So we get r is x plus s over 3. And now that we have s, we can plug it into that equation. Here is S. We'll plug that in here. And then let's simplify. And we get 5 over 13x minus y over 13y. Okay, so now let's see if these expressions for R and S will get us x, y, z. Okay, so here's our S, 2 over 13x minus 3 over 13y. And R is 5 over 13x minus 1 over 13y. Let us now plug in R and S into this linear combination. Okay, so here is the R and here is the S, and let's simplify it. What are we going to get? So let's actually do the multiplication by hand. We need to multiply this scalar into the 3 components. So I'm going to copy that, and I will multiply it by 3, so that becomes 15 and 3. And then we will multiply by 2. So now we have 10 minus 2, and multiply by 1. We don't have to do anything. So let's do the same thing here, where we have to multiply this scalar into the vector. So first we will multiply by negative 1. So we get minus 2x and then plus 3y. And then by negative 5. So we are going to get negative 10 and positive 15. And finally, we will multiply by 2. So we are going to get 4 minus 6. Okay, so we are now going to combine these two vectors. What are you going to get? Well, we are going to get 15x minus 2x, so that's 13x over 13. Oh, so that's just x. And we have minus 3y. Oh, but there's a plus 3y here. So those y's are going to cancel. So we just get, for our first component, we just get 13 over 13x, which is of course just x. Second component, we have 10x over 13. Oh, but there's a minus 10x over 13. So those cancel. Minus 2y over 13 plus 15y over 13. Ooh, so that is just 13y over 13. So, how about the last component? We get 5x over 13 and a 4x over 13. Uh-oh, that is a 9x over 13. Minus y over 13 minus 6y over 13. Uh-oh, that is a minus 7y over 13. Oh, but wait a minute. Oh no. But we saw earlier that z is just 9x minus 7y over 13. So that whole vector just simplifies to x, y, z. So what we have just shown is that if x, y, and z satisfy the Cartesian equation minus 9x plus 7y plus 13z is 0, then we can find R and S so that x, y, z is R times 3, 2, 1 plus S times minus 1 minus 5, 2. And so we can put those two statements together into a single if and only if statement, namely, a vector xyz in R3 is in span of 3, 2, 1, minus 1, minus 5, 2, if and only if the components x, y, and z satisfy the equation minus 9x plus 7y plus 13z is 0. So again, we call minus 9x plus 7y plus 13z equals 0 a Cartesian plane for the plane span 3, 2, 1 and minus 1, minus 5, 2. So why is it that we call it a Cartesian equation instead of the Cartesian equation? Well, that's because this equation is not unique. We can also write it instead as positive 9x minus 7y minus 13z is 0, or multiplying by negative 2, we get minus 18x plus 14y plus 26z has to be 0. Okay? So another way to write that statement that we just saw is that the span of these two vectors is the plane in R3 with Cartesian equations minus 9x plus 7y plus 13z is 0. So we can generalize this example and use it to define what a plane is in Cartesian space. If u and v are vectors in R3 which are not parallel to each other, then the span of u and v is a plane capital Pi in Cartesian space that passes through the origin. It has a Cartesian equation with the form ax plus by plus cz equals 0. And the constants a, b, and c have at least one coefficient which is not 0. They cannot all be 0. So in other words, there are scalars a, b, and c, not all 0, so that x, y, z is in the span of u and v, if and only if ax plus by plus cz equals 0. All right, so we have reached the end of our video. You can find me on Facebook. You can find the 4th edition on Facebook, and you will also see it at my homepage at kendallhunt.com. So until our next video, thank you for watching. Goodbye.